Hello, today we're going to be reviewing the use of the quadratic formula and specifically how the discriminant within the quadratic formula can be a very useful tool and tell you quite a bit about the shape of your parabola and where it sits on the graph. So this formula, at this point in time, I'm going to be assuming that you have memorized it and that you know it. If you haven't, then please take some time. It's a tool that needs to be in your math toolkit, that just as important as being able to factor. And speaking of factoring, if you are asked to solve a quadratic equation, this is a quadratic function. F at x is equal to 2x squared minus 4x minus 6. If I was asked to find where that is equal to 0, then factoring, first of all common factoring and then trinomial factoring, is a very quick and easy way to find roots that are nice integer values or nice values of a half or a third or 3/2, those kinds of things. When I have a quadratic equation that is factorable, then those factors, if I set it equal to 0 to say, hey, where does my equation not go up or down, has a y value of 0. A y value of 0 can be achieved with a 3 in this first factor, which corresponds to this root at 3, and a -1 in the second factor. If I put -1 here, I get a -4. But a 2 times a -4 times a 0 zeroes out the whole side and has a y value of 0. So if you use an input of -1, you get an output of 0. And when our roots, our x-intercepts, our zeros, three important names for the very same dots on the graph, when they are nice, easy integer values, that means that a quadratic function factors nicely. However, you will have situations where you won't get such nice roots or zeros or x-intercepts. This one looks like a nice easy -3. However, over here you can see that this root, well, that's between a 2 and a 3. It's a 2 decimal something. And those values are not easily identifiable by factoring. And so we have another tool, our quadratic equation, that helps us find those values that are perhaps decimal values. We can use the quadratic equation. Now, the quadratic equation is useful. It could find the 3 and the -1. It's just overkill. It's a longer, more tedious method to find the zeros, but it would work. I could put a 2, a -4, and a -6 in my quadratic formula and calculate out the 3 and the -1. But factoring is just a faster way to get there. Now, what I want to do is really focus in on part of my quadratic formula, the part that we call the discriminant. It's the part under the root sign. It doesn't include the root sign. It's the part under the root sign. And it can tell us an awful lot about the way our parabola sits on a graph. For example, if I was to use this one to solve my quadratic function, I would sit there for a while and see if it factored nicely, and it doesn't. And so because it doesn't factor nicely, I always check that out first. I would use my quadratic formula. I would say, okay, well, my a value, the value that's sitting in front of my x squared, we have our general formula here in standard form. The number sitting in front of x squared is indicated as a, the number sitting in front of your x term is b, and your constant all by itself is represented by c. And so in this particular quadratic equation, I have a 2 for a -5 for b, and c is equal to a -11. So when I run this through the quadratic formula, x equals -b plus or minus the square root of my b squared value minus 4ac under that root sign, the discriminant under the root sign there, all over 2a. In this particular case, when I have a -5, that will become a +5, plus and minus the square root of a -5 squared minus 4 times an a of 2 times a c of -11, all under that root sign, all over 2 times a 2a, or a value. So I have 5 plus and minus the square root of 113 all over 4. Now, what I want to notice is this number here. Can I take the square root of 113? I absolutely can. It's not a nice number. It's a decimal value. I'll be taking it, adding it to 5, and the second time around I'll be subtracting it from 5, getting a decimal value, dividing by 4. In fact, this tells me that I have 2 answers. If I am asked for the exact value of my roots, well, one of them is 5 plus the root of 113 over 4. Excuse me. And the other one is 5 minus the square root of 113 over 4. And those are my exact values. And the only way I would adjust that is if there was a perfect square hiding under my root sign. Let's say there was a factor of 4 or 9 or 16 in my 113, then I would reduce it out and I would have a fully reduced radical there. But there is no perfect square factors in a 113, and so I'm done. And if you run that through a calculator, 5 added to the square root of 113 divided by 4 is...
Please come to the foyer, your right is here. Up to the foyer, your right is here.
That comes to approximately 3.9. And this one over here, if I take 5 minus the value for the square root of 113 over 4 in my calculator, it's approximately a negative 1.4. What that is telling me, if I was to sketch this curve, and let's do it down here, it tells me that I have a not so nice number root as, let's say that's negative 2 and that's negative 1. It's at a negative 1.4, probably about there. And if I have 1, 2, 3, 4 for my scale, then my other root is at a 3.9-ish. And from my quadratic equation, I know that I have an a value that's positive, so I know that this parabola opens up, and so I could sketch it in this manner. Notice that my discriminant, the b squared minus 4ac portion, that came out to 113. Because that is a positive number and I can take the square root of it, I have 2 distinctly different, so 2 distinct real roots, real number roots. Real number roots means that those numbers exist in the real number system. They are numbers that can be found on a number line. They could be positives, they could be negatives, they could be decimals, they could be fractions, but they're in the real number system. And this always happens when the discriminant is a positive number. You can count on that. You get a positive number under your root sign for the discriminant, you will have 2 distinctly different real roots. By the way, if I got a nice perfect square under that root sign, let's say it was the square root of 4. Well, the square root of 4 has a nice whole number value. It's a 2. And so I would have 5 adding 2 over 4 and 5 subtracting 2 over 4, 2 easy, nice roots. If I get a perfect square for my positive discriminant, it means that this thing was factorable. They're not decimal values. There could be fractions, but they were fine. You could have found those roots by factoring. Okay, let's take a look at a different situation. I can't say that my c value is positive 18 because it's on the other side of the equal sign. I need to get my entire quadratic expression on the same side of the equal sign, so minus 18 equals 0. Then I can say that a is a negative 2, b is a 12, and c in fact is a negative 18. When I run that through the quadratic formula, so negative b would be negative 12, plus and minus the square root of b squared, so that would be 12 squared minus 4 times a times c. Notice I have a negative, negative, negative. I'm going to be subtracting from my square value. And so all over 2 times an a value of negative 2. This comes out to...
This car's called 500, please. This car's 500.
A negative 12 plus and minus the square root of 144 minus 144. I get plus and minus the square root of 0, all over negative 4. The square root of 0 is a nice easy 0. And we don't really talk about an addition or a positive 0 and a negative 0, but I do have to add it and subtract it with my formula. And so I get x equals a negative 12 plus nothing over negative 4. Well, that's a x equals 3. And if I have the second root, it would be an x equals negative 12 minus nothing over negative 4. Well, that would also be a 3. And the way that that works for a quadratic equation, this was factorable, it's a nice easy square root, it would have come from the factors of x minus 3 times x minus 3. And remember, I had a leading coefficient of negative 2, so I would have had a reflection and a stretch factor, so that would still be out here. I would have had an equation y equals negative 2 x minus 3 times x minus 3. I still have two roots. It's just that they're equal to each other. And so this curve, this sketch, might look like this, where I've got one root and two roots. This one has a negative leading coefficient, so I know it opens down. It might be something that looks like this on the graph. But the point here is, if your discriminant comes out to being 0, you have this kind of parabola with its vertex right on the x-axis. You have two equal, there's still two roots, I know it looks like one dot, two equal real roots when the discriminant is 0. All right, last one. I bet you can probably figure out what's going to come next. Let's bring my 5x and my negative 15 over, so I have my expression all on one side of my equation. Add them, subtract it, and add it to both sides of my equation. I have an a value of 1, a b value of negative 5, and a c value of 15. When I run those through the quadratic formula, negative 5 would be 5, plus and minus the square root of b squared, well, that's 25, minus 4 times a, well, that's still 4, minus 4 times a times c. 4 times c is going to be a 60, all over 2 times a, which is just 2. And so I have 25 minus 60, that's negative 35 over 2. Now, when I had a discriminant that was a positive number, I could take a square root and get two equal real roots. Two distinctly different real roots. When I had my discriminant be a 0, then I had two identical real roots, but this is an imaginary number. I cannot take the square root of a negative number in the real number system. This is an imaginary number, the square root of negative 35. And not imaginary like Peter Pan Fantasyland imaginary. I'm talking about a number in the imaginary number system. And so if I was to quote my two exact roots, they would be x equals 5 plus the square root of negative 35 over 2, which does not exist on a number line because you cannot find the square root of a negative number in the real number system. 5 minus the square root of negative 35 over 2. And so I get two imaginary numbers with a discriminant coming out to be a negative 35. So we get two imaginary roots. And this happens with a discriminant that is negative. What does that mean about my sketch of my parabola? Well, what can I count on from this equation? Well, I can count on the fact that it opens up, and I can count on the fact that it has a y-intercept of 15. So if we say that, okay, that's 15, and I'm opening up, but I have no real number roots, perhaps my parabola is doing this, or maybe it's doing this. I'd have to sleuth it out a little bit more, but I am not touching my x-axis. I have no real roots or x-intercepts. Okay, so let's use that information use only the discriminant to determine the nature of the roots for each of the following. Okay, so we look at this and we say, well, if I'm going to get my A, B, and C value, I better do some simplification of this. Please don't tell me that this is x squared plus 1. I get a lot of times people losing their middle term from this expression. You're truly foiling this out by binomial expansion. I get x squared minus 2x plus 1 is equal to 2x minus 3. Let's bring all of our terms to this side. Negative 2x that was here, another negative 2x plus 1 that was here, add the 3 that came over. I get x squared minus 4x plus 4 equals 0. Now, truly, I should go and see if that factors, and it does, but I do want to talk about, it told me that I had to use only the discriminant to determine the nature of the roots. That means how many, or what type of roots do we have? Do we have two distinctly different real roots, two equal real roots, or do I have two imaginary roots? And so my A value is 1, my B value is negative 4, my C value is a 4, and if I just use the discriminant, and my discriminant is b squared minus 4ac. If I just use my discriminant, b squared, so I got negative 4 that is squared, minus 4ac, so 4 times 1 times 4. I get negative 4 squared is 16, minus 4 times 4, that's minus 16. Hey, that's 0. So what does that tell me about this particular parabola? It tells me that I have a parabola that has two equal real roots. So therefore, two equal real roots. I perhaps, and in fact, if I did factor this to find out where those roots are, I would say that I would have x minus 2, my roots are at x is equal to 2 and x is equal to 2 right on top of each other. And so this sketch would look something like this at 2. I know I'm opening up because of my leading coefficient, and so perhaps I've got something like this as a parabola with two equal roots. There's one, there's another one right on top of it, and we can see that it comes from the double factoring situation, one from each of the chances of making a 0 in the equation. All right. When I have a fraction, the easiest way to get rid of that denominator is to multiply it to the other side, or we can think of multiplying both sides of my equation by 2. So I'm working with a negative 2x squared is equal to, my 2's cancel out here, so I've got negative 5x plus 5. Now, I could either bring all of my terms over here and deal with a negative a, or I could bring my x squared term over to the other side and deal with a positive 2a. Either way, you're going to get the same conclusion in the end. Minus 5x plus 5. Let's do this approach. My a value is 2, my b value is a negative 5, my c value is 5. My discriminant, b squared minus 4ac, well, that would mean I would have a negative 5 squared minus 4 times a 2 times a 5 as my c value. I get 25 minus 40. I get a negative 15 as my value for my discriminant. Well, remember, in my quadratic formula, the discriminant is under the square root sign. So a negative 15 under the square root sign would create something that is not making a real number in the real number system. And so, therefore, I would have two roots, but they're imaginary numbers. I know that I have a parabola that's opening up in my situation, so perhaps I would have, I don't know, maybe something like this. I would have to figure out where the vertex is, but it would be not crossing the x-axis. Sorry, I was going with that negative if I brought it all over. This one has perhaps a situation like this, where I have a vertex somewhere, but not crossing the x-axis. Two imaginary roots. All right, these terms are in a little bit improper order to be able to consider it easily as a quadratic. When I rearrange it, it becomes apparent that I have an a value of -3, a b value of -2, a c value of 1. When I run that through my discriminant, b squared minus 4ac, I have a -2 squared minus 4 times a -3 for a 1 for c. I get 4 plus 12. I get a nice 16 that is going to live under my square root sign in my quadratic formula, because remember my quadratic formula, the discriminant we have been figuring out, we are then going to go and take the square root of. So it's a positive value. It has two, so therefore I have two distinctly different real roots. You could say two distinct real roots, two different real roots. And also, since it's a nice square rootable number, it's a perfect square. Since the discriminant is a perfect square, the equation was factorable. You didn't need the quadratic formula, or you don't need the quadratic formula to give you any rotten rounded decimal roots. They'll be nice numbers that you can find by factoring. But the big picture idea here is that when you are talking about, hey, what value do I get under this root sign, it tells you an awful lot about the position of your parabola. Perhaps you've got two distinctly different real roots across the y-axis here. If you have a positive number for your discriminant, then you will have two different real roots. If you have a negative number for your discriminant, you will have no real roots. You will have two imaginary roots. And if you get a 0 for your discriminant, it means that you have two equal roots right on top of each other there. So let's use that in a little bit of a different way. Make us think about, what if I didn't know one of the values, the a, b, and c values? Now I have a situation here where I'm looking at a family of curves that would share a certain set of characteristics, but I have the availability or the option of putting in different numbers for k. I want to know, of all the numbers that I could put in for k would create all kinds of different parabolas, but which numbers would create a parabola that has non-real roots? Well, that's just another way of saying imaginary roots. So some of the numbers that I would put in for k would create a situation like this. Some of the numbers that I could put in for k would create a situation like this. But I want to know what numbers for k would create this situation, parabolas that don't cross the x-axis. Well, what I do know is if you want a parabola that has two imaginary roots, no real roots, you need to have a negative discriminant. And so your discriminant must be negative. Which means b squared minus 4ac must be, how do I show negative? It has to be less than 0. Numbers less than 0 are negative. Well, in this equation, I have an a value that's unknown. I have a k standing in for my a value. I do know my v value, it's -2, and I do know my c value, it's 1. So in my b squared minus 4ac, let's substitute in those numbers. I've got -2 that's going to be squared, minus 4 times an a that I don't know, I have a mystery value, times a c of 1. All of that has to be less than 0. So let's simplify this up. This is 4 minus -4 times a 1, that's 4k, is less than 0. Now you might look at that and by inspection you might say, well, 4 take away a mystery has to be less than 0. Well, if this was a 1, if k was a 1, then I would have 4 minus 4 would be equal to 0. So that didn't satisfy this being less than 0. What about a 2? 4 minus 8, that would be less than 0. What about a 3? What about a 3.7? What about a 10.8? Anything bigger than 1. If I put less than 1, hey, let's put a negative number. Like, let's pick a negative 2. Then 4 minus a 4 times negative 2, that would be a plus. And I'd get a whole positive value here, and that's not less than 0. And we can solve it by inspection. But when the numbers get a little crazier, what we can do is treat it like an equal sign. Treat it like an equal sign and solve. So let's pretend that's an equal sign and let's solve for k. Now, first of all, what I want to do is add this negative 4k to both sides so that it becomes a positive term. There is one more rule to solving equations with an inequality, and it has to do with dividing by a negative number. So I don't really want to kick this 4 over here and then have to divide by a negative number. We'll discuss that a little further in the course, but for now, if I add to both sides, I can keep my inequality the same way, and then I would divide away my 4, and I would say, oh yeah, there's my k, and there's my 1, and I would have to read it backwards to read this inequality, so I could flip it around, and k has to be associated with the open end of the inequality, so k has to be greater than 1. So I could make all kinds of parabolas by sticking in all kinds of numbers here. But if you want a parabola that has no real roots, 2 imaginary roots, this kind of situation, then you have to pick k values that are bigger than a 1. Anything bigger than 1, and you'll get parabolas like this. Anything less than 1, and you'll get other parabolas, but you certainly won't get this situation. Okay, one more step different. I have got that same mystery number, but in 2 spots this time. And I want to know when will they have equal roots. So I want the situation where I have a parabola. I know I need a discriminant equal to 0 to create a situation where I have a parabola with 2 equal roots on top of each other, perhaps opening up, perhaps opening down. But of all the numbers that I could stick in for k, I want values of k that will create parabolas where my vertex is on the x-axis, so I have 1, 2 roots on top of each other, equal real roots. Okay, well, let's look at it in the very same way. Here I have an a value that's 2, a b value that's a mystery and it's a negative mystery number, and a c value that is just the very same mystery number but a positive version. I know that my discriminant, b squared minus 4ac, in order to have this situation of 2 equal real roots, it has to be equal to 0 under that root sign. Let's sub in our values here. For b, I have a negative k minus 4 times an a value of 2 times a c value of k. Clean this up a little bit. Negative k times negative k would be k squared minus 8k is equal to 0. And now I have a quadratic equation. I'm going to solve that by factoring. Well, I've already set it equal to 0, so now I factor. And I find that the value that would create a 0 out of this side, this one, a k value of 8 in here would make a 0 times 8. And a k value of 0 here, I get a negative 8 here, but 0 times negative 8 would be 0. And so I would have a situation where I could create only 2 equations. You would have to put a 0 in here, which in that case you would have a parabola y equals 2x squared, and that would look like this. I don't go left or right. I would have a parabola on the origin, or with a vertex on the origin, 2 real roots right on top of each other. Or if I put an 8 in there, I would get 2x squared minus 8x plus 8. That would also create a parabola that had a vertex on the x-axis with 2 equal real roots. So therefore, k values, I only get 2 values that make this work. K values of 0 and 8 create parabolas with 2 equal roots. Whereas, oh, I forgot to write a therefore statement. Over here, I had a whole mess of numbers, not just two distinct numbers that created two equations that had two equal roots. In this situation, anything bigger than 1. So over here, therefore, any number larger than 1 creates parabolas, lots and lots, infinite number of parabolas with imaginary roots. All right, so what I'd like for you to do is to finish up your homework. Hopefully that helps with the idea on the front of your riddle sheet homework. Where do you find sculptures of great baseball sluggers? Now, a little bit of a different terminology here. We've been talking about two equal real roots. You can take a look at this one and see that on the x-axis, I have my vertex on the x-axis. What that truly means, if I was to factor this equation, I would have x minus 2, x minus 2, two equal real roots. This riddle sheet, however, has you asking how many solutions to this equation. Well, there are two equal real roots of x equals 2 and x equals 2 sitting on top of each other, but that really is one solution. It's a 2. So the solution of 2, one solution of 2 creates the 0 over here. So I have one solution, but two equal real roots. One solution to the equation. It's a 2 in here and here that makes a 0, but that means that I have two equal real roots. This sheet talks about the solutions to the equation. So over here for question 1, we have one solution, so I would circle the letter in the one solution, and my riddle is going to be made up of these letters. So you can do that visually, finding one solution, two solutions, or no solutions to the equation. Over here, we have no solutions to where this parabola is equal to 0. It never hits a y value of 0. And so there's no solutions. But what that means is we have two imaginary roots. So keep track of that terminology. All right. Down here, it says use the discriminant to find out how many solutions. It's different than the number of roots. We'll either have no, one, or two solutions, but we always have two roots, whether they be real roots or imaginary roots. A little bit of thinking down here in the bottom, and then over the page is just using the quadratic formula to find the roots. So lots of good drilling on that. Please make sure that you come to class next day with all of that practiced up so that we can move to the next step. Thanks, guys. See you soon.